Okay, we are now looking at one of the topics in operation research. Okay, then the topic is called queuing theory. One of the independent topics. There are only about 6 topics in OR. The first one is our LP, linear programming. Then the other one is transportation. Because for this class, we are going to have at least 25 to 30 minutes. So the second topic is transportation, and these topics are independent of each other. Then number 3, we have networking. Then the other topic that we have in operation research is assignment problems. Assignment problems. Then we have the other one, which is queuing. So the other one is queuing theory. And then the other one is simulation. So these are the topics that are covered in operation research. Okay. So once this is covered, then everything else will be okay. Of course, there may be another topic here called decision theory. Okay, for minimax and the max. So these are only the topics that are covered in this operation research. All right, so now getting down to the queuing theory, we look at so I selected queuing, one of the shortest possible topics because of this time, because the class would only run up to 21:15, somewhere there. All right, so under queuing, we have the aspect. So in queuing, we look at the probability of queuing, PO, probability of queuing is equal to average arrival rate over service rate. PO is a probability of queuing. So our lambda is average arrival rate, average arrival rate. Then this one is average service rate. It's called the mu, okay, which is average service rate. So average service rate. So this one is on average what? Service rate. So what we are simply saying is that the service rate should be more than arrival rate if we are to manage the queue. Queuing theory is found in almost every organization. Okay, so it's found in almost every organization, in banks, or in everywhere else. So probability of queuing, that is the formula there. Probability of there being any customer in the queue is equal to 1 minus PO. So 1 minus PO, then PO to the power N. So N is representing the number of customers. So this one is representing number of customers. So this is on probability of there being any customer. Okay. Then probability of not queuing. So probability of not queuing. So not queuing is given by 1 minus PO. That's not queuing. Then now getting down to number 4, length of the system. The system, LS simply means length of the system, is equal to lambda over mu minus lambda. And then the lambda and the mu should be in the same denomination. Lambda and the mu should be in the same denomination. Should be in same denomination. Okay. Same denomination. What it means by denomination is that it should be per hour, or per minute, or in the same units. They should be in the same units. Then we have the other formula. There are only 7 formulas here for queuing theory, and the topic is over. Time in the system, the time that you spend in the system, that is in the time you spend in the bank or at an office when you go for a service, is given by this one. Then we're getting down to the other one, where we are looking at the other one, which is length of the queue. Length of the queue is equal to lambda square over mu, the mu minus lambda. The last formula here is aspect of time spent in the queue. Time in the queue is equal to lambda over mu, then mu minus lambda. All right, so this is what is involved in queuing theory. So when the queue is forming, when queue is forming, so when the queue is forming, our arrival rate is actually less than, when the queue is forming, our arrival rate is greater than our service rate, because you find customers waiting for you before you open your premises. And then after queue is formed, after queue is formed, the arrival rate should be less than the service rate. In fact, the service rate should be more than arrival rate in order to reduce queue size. So in order to reduce queue size. Okay. So this is what is involved in queuing theory. So getting down to the example, we can have a counter at the bank branch performs the transaction with a mean time of 2 minutes. Okay, the customer have arrived at a mean rate of 20 customers per hour. Okay, so they arrive at 20 customers per hour. That's the arrival rate. So our lambda is equal to 20. This is 20 per hour. So meaning that if we assume that follows the Poisson process and that service time is exponential, okay? So meaning the counter at the bank branch performs transaction with the mean time of 2 minutes. So meaning we're able to serve a customer in 2 minutes. All right, so meaning that per hour, how many are we going to attend to? So how many customers are we going to attend to in an hour? So this is about what we need to find out now. Okay. So we need to find out the arrival rate is 20. For that question, arrival rate is 20 per hour. So the service rate, one customer takes 2 minutes to be attended to. Okay, one client. Now, how many customers will be attended to in an hour? An hour is 60 minutes. So our 2x is equal to 60. So the service rate of a cashier will attend to 30 customers in an hour. So meaning our service rate will be 30 per hour. This is not bad. It means that this cashier will be able to manage this queue. All right. So this is about what is opening. And from here, we can start now solving this problem. So probability that the bank teller is idle. This is the probability of not queuing. All right. So probability of not queuing means that these ones are idle. All right. So meaning here, first to find probability of queuing, our service rate for this problem is what is important, which is a 30 from the workings per hour. So from here, you can substitute and get whatever we need. So the first one is asking us to find the percentage of time the bank teller is idle. So other questions in this pamphlet, as much as what the concept is understood for the same 7 formulas that we have there. Okay. Then we just need to look at it that way. Okay. So okay. This is about, okay. So this is about what is so this is about what is happening here. So now getting down to, for as long as we have these ones, it's very easy now. If the probability of queuing now is actually going to be equal to the first one, the probability of queuing, it is lambda over mu. So these formulas are given. So it will be 20 over what? 30. So that is the answer that will be number 1, probability of queuing. Not queuing simply means idle. Not queuing. So it is just the opposite. So this is about what is going on as we look at this one here. Okay, so 20 divided by 30 is 0.67. So not queuing is 1 minus the 0.67, which is what? 0.33. So idle or not queuing. So this is about what is going on. Then time in the queue, the formula is lambda over mu, then mu minus lambda. So just substituting these figures here, we are getting the value of anything else that you can actually get, for you to get the value. So it will be 20 over 300. That's the time in the queue. All right. So here in queuing theory, one of the very interesting topics and very short topics. It was a very short topic, one of the shortest topics in form in operation research is queuing theory. So if we go for the other one is the length of the queue, okay, or how many customers are in the queue. It is just a matter of using the formula. Okay, so this is the formula to use when getting to, so it will be 220 square here, then over 30, then 30 minus 20, which would be 400 over 400 over 300. So this is what goes on. You can find the answer like that. When you're finding the time in the system, time that a customer should wait in the system is just seated in a bank, is not in the queue, is just given by this formula here. So that's why I mentioned that this is one of the, this is the length of the system. Okay, so this one is the length of the system, how many customers are in the system. Okay, so how many customers are in the system? They are just in the bank there, they are not in the queue. They are just seated in the system. So there are two customers seated in the system. Okay, so this is about what this queuing theory involves. Then the time in the system, okay, it's 1 over mu minus lambda, which is 1 over 30 minus 20, which is our time in the system is actually 1 over 10. Okay, so this our time in the system will be is equal to 0.1 hours. So 0.1 hours. Okay, if we multiply by 60, it will give us the, convert to minutes to be approximately almost just 6 minutes. Okay, this is what this queuing theory is all about. All right, so it is equal to 6 minutes if you are to convert these in minutes. So this is what goes on. So queuing theory is not a complicated topic in operational research. It just goes with the following the standard rates. These are supposed to be per hour. Even this other one is per hour. If it is in minutes, you need to convert it into per hour so that we find what is going on. Now, if we ask the question that what's the probability of there being one customer, so there being n is equal to one customer, in fact 4 customers. So Pn is equal to, okay, 1 minus Po, then Po to the power n. So P4 is actually equal to 1 minus the 0.67, and of course the 0.67 outside here should be raised to the power. So 0.67 to the power 4. So this is what goes on as we are looking at the probabilities of there being any customer. N can be 4, can be 5, according to what the examiner can actually talk about. So this is it on what this one requires. All right, so please take note of the fact that queuing is not a cumbersome topic. So meaning that all other questions coming in this pamphlet, by virtue of just getting down to these simple formulas, you'll be able to, there be 4 customers, all these is not an issue. You need to attend to it. Okay. So this is okay. So you need to make sure that we convert these in appropriate standard hours. They're supposed to be in hours. All right. So meaning we have even this other question, 2, we need to make sure that we actually sort out customers arrive on average 7 in every 4 minutes. So 4 is equal to 7. How many can arrive in 7 arrive in how many minutes? Now, what about in 60 minutes? How many will arrive? So it will be 4x is equal to 60 times 4. That's 60 times 7. Then divide by 4. You use this mathematical equation to find these the denominated in per hour. So this is how you find these ones per hour. You convert them into per hour. So it will be 60 multiplied by 7, then divide by 4. It's 105. So our lambda will be equal to 105. Then from here, we can now go for the service rate. Okay, the cashier can save 9 in 4 minutes. So even here, you have to find that combination. Arrival rate is 105 per hour. And then the service rate is 9 in 4 minutes. So 4 minutes is equal to 9. In 60 minutes, we are going to say x. So as we cross multiply here, it will be our 4x is equal to 60 by 9. Then you can find that, and after finding these, we can use the formulas to actually calculate whatever we need. So this is about what goes on here as we sort out this one. Everything else, so it's 135 customers per hour. So please take note of this. And then from here, we can find probability of queuing by simply saying lambda over mu, and then you substitute the 105, then over the 135, and all other things will be sorted out as we break down using these other formulas that I had just given from the starting point of queuing. This one is found in every organization. This is the reason why we are doing it. So this is a very important topic that we need to actually attend to. So all other questions can be resolved. So the other question is coming in this pamphlet. For as long as you understand how to go about it, this topic is not an issue. You need to go through and understand it. Unless there are questions so far. Are there questions so far? If you have no questions, please take note, take time to go through this, whatever it is that we've discussed this evening. If there are any other issues and queries, we'll be able to attend to them. So we can end the class for now. So all these ones, they are here. You can go through the recordings or anything else you need. And then in the next class, we'll be able to attempt the other questions that are there in the pamphlet. So this is where we can end for now. Of course, the basics, I've explained already the basics where the queuing theory is coming from the, all right, so we can end here for now.